Morning, Chris. So today we will discuss on the remaining networking part. So if you remember in the last class we discussed about the communication of the pod. So we discussed on the pod to pod internal communication within the same host. We also discussed about the pod to pod communication between two different hosts. Then we discuss on pod to outside communication and outside to pod. See, outside to pod and pod to outside is just like a two different directions. So here we discuss that if you communicate within containers, if you are talking, so it's using the local IP, that's loop back interface 127.0.1. In this case, there is no external IP communication required for the pod because two containers within the same pod are going to interact with each other. But when a pod try to communicate with another pod, and if it provided it is in the same host, in that case you can see there is an interface. We call it as virtual interface. Every pod has a virtual interface created by the Kubernetes architecture. So here this VETH0, which belongs to pod A. Similarly, VETH1 belongs to pod B. So if pod A and pod B in the same host are trying to communicate, they can directly talk to each other without any external, any kind of networking device except for the bridge. So this bridge you see is something which is providing a connectivity between two pods. So you don't need to go to proxy and IP table services because your packet is not going to land outside. Then there was a case where we have to see the pod to pod outside node communication. In outside pod to pod communication, we draw this diagram. So here we just categorize on the different colors. So first one was container to container within the same pod. Second one was your pod to pod within same host, then pod to pod on two different hosts. So when I say pod to pod on different hosts, this that means that your traffic is going out from pod A. So here suppose pod A deployed on node 1 and pod C deployed on node 2. So green color you can see this pod IP is going to talk to the internal. So there is a virtual interface. Then you have a bridge, and then from there it goes to proxy, and then proxy it goes to IP table, then IP table it goes to host interface. This host interface is the final, you can say, port, sorry, final exit point from your node. So from there it will go to some outside cluster, and then from their cluster it will again come back to the second node. So when it comes to the second node here, when it comes to second node, okay, so here it was, then it will land to the node 2, and in node 2 it will go to the IP table, and then based on proxy it will again go to the bridge, and then it will finally land to the node 2 port. Then there is a pod C. For outside communication, this is you can see this is the purple color where this is going outside of your node. When it goes outside of your node, so here you see this nick, which is we call it as the nick of your node. So this is worker node nick port. So there is no routing, involved at this point, which will tell the packet to go outside on which destination. Everything is decided based on the IP table. So here you see this is something called IP table. This IP table is very interesting. It will let you know your service, your traffic should go to where. So I told you one thing about service. So I mentioned you that there is something called service. So what exactly is a service? So let's say this is your node, and this is your NIC port. So this is your NIC. Just a minute. Okay. So let's say this is your node and this is your port. So here you can see this is your NIC port. Similarly, this is your, you can say, worker one. Then suppose this is your pod. Here you have some container running, and then you have a requirement to go outside. So your packet is supposed to go outside. So from this point, you need to land to this NIC port. That is your actual requirement. So this is called your pod So this is called as your pod interface, and this has some IP. So you definitely have some IP1 for your pod, and this IP belongs to the internal networking. So this IP you need to go to this final NIC port. In between, you will see there is something called bridge, something called as virtual bridge. Then you have something called proxy, and then you have something called as this is called as your IP table. This is called as the IP table. This is called as your proxy. Now this IP table, because nobody knows that the packet is actually going to land outside or it is going to land to your internally within the cluster. So there is something called as service. So you define something called service. This service is very important because this service is going to decide your destination. So you can call it as a kind of a router. So if you have to like understand, this is called as a virtual router. This service is basically a virtual router, and it will send your packet. So see, this is the physical part. So this is your physical connection. From here, it can go outside, but this service will tell that this packet should go to which particular gateway. So the gateway definition, or you can say that the traffic direction is decided by this service. This service is of three type. One is your cluster IP. So suppose if your service is say cluster IP, that means your destination will be, so it will be to your second node. Suppose so it will be meant for your some other node within the same cluster. So suppose let's say this is a cluster and this has three nodes. So it is a three node cluster, and this cluster IP, so all the NIC ports, so you can see this will be going to this. This will be going to this. So if you have a cluster IP, if your service type is cluster IP, so these are different type of services you can define. So you have cluster IP, that means this particular service will get one IP, and that IP will be called as cluster IP, and that IP will be accessible only from inside, accessible within cluster. It is accessible within the cluster. Means if you
Why they
try to, yes.
why they call it cluster IP?
See, we call it as cluster IT because this is meant only for internal communication. So, if a layman want to understand that what exactly this cluster is, so just think of it like you have multiple nodes. All of them are interacted. All of them are talking to this particular router. So, let's say this is a router, and this is an internal router. Internal. So, all of them are connected to this router. And if anybody want to talk to each other, so suppose some packet from here is meant to for this destination, then it will travel from here. So let me put some different color. Okay, so suppose from here, so internally it need to follow the same path. If you remember, I told you that within a node there is a specific path that from your pod. So let's say your traffic will go from your pod. So this is your pod. So this is your pod. Then it will go to the virtual bridge. This is virtual bridge. Then it will go to proxy, which is Q proxy. Then it will go to IP table. So IP table is something your rules, which will tell that okay, this particular request should go to which particular destination. So here you basically have rules for destination. for source, destination, protocols and ports. Everything is mentioned in this IP table. And then you go to the final NIC port. So this is your NIC port of your worker node. So this is the internal architecture. So if you see, this is an internal architecture. This one here is totally internal. This is internal, this is internal, this is also internal, and this is also internal. But this is your gateway, kind of a gateway of your worker node. So if your packet is meant to go outside your worker node, then there is something called this IP table will route you to some service. So when a packet is coming based on the destination, so here it will see what is your destination, and based on that destination, it will route to the specific service. So suppose you define, for example, three services. So service one, service two. So let's say two service. So one is your cluster IP, and then second one suppose is your node port. So when you say node port, means that in this particular node, a dedicated port will be allocated for you. A virtual port will be created. Virtual port. Virtual port on the same NIC card. So you have a NIC interface of your worker node. On that there will be your dedicated port. So what will happen, your IP table will see what is your destination. So if your destination is cluster IP, that means your request should go on this particular internal VLAN. So you can assume this cluster IP as an internal VLAN for pod. So in that case it will take this route, and then it will go to the next node. So here, if you imagine, so this was the internal call flow, internally within a node. So when you have this cluster IP means that you have a IP allocated to your service. So you imagine it like your service. So there are so many services running. This is your pod service. This service is your pod service. So suppose you created a GUI pod. You create a GUI pod. So for that GUI pod, this particular service which you have created, it is going to have some IP. So let's say that IP will be 192.168.10.16. So this IP is a cluster IP. This is a cluster IP. And if somebody want to connect internally, they need to use this particular IP. See, this IP does not mean that it is a VIP IP. It is not a virtual IP. It is, you can say, an IP has been given to this particular, it act as a gateway. So all the internal traffic will go to this particular gateway. And from there, it will go to the next destination pod. So let's say, let me try to draw one diagram. So let's say you have a pod 1. So you have pod 1 and the IP is 192.168.3.7. Then you have pod 2. The IP is 192.168.3.9. And then you have something called pod 3. The IP is 192.168.3.15 because it's from the same network. Then you create a service for these pods. So suppose these pods belong to some specific service. So you create a cluster IP. You create a cluster IP service for this pod combination. So these pods, for example, belongs to GUI. So let's say it is a GUI pod. So for GUI pod, you create a cluster IP. So that IP will be something like 192.168.3.18, something 18. That will act as a kind of a gateway. So it will become as a gateway. Now, so
Does it
this,
have to be on the same network,
yeah, it
or it
will
could
be
be
on the
different?
it will be on the same network.
Oh, it
So
has to be
here
on the
you,
same network.
yeah, see it, everything is on the same internal networks. There is an internal network of your pod. That same network is being used for as a cluster IP also. So what happens that, for example, this particular pod is on node 1. This pod is also on node 1. and this pod is on different node. So let's say it is on pod, this is on node, some different node. So let me call this is on node 1, this is also on node 1, but this one is on node 2, which means that packet need to go outside of your node. So if pod 1 talking to pod 3, pod 1 talking to pod 3. So if your pod 1 need to talk to pod 3, then 192.168.3.7 need to talk to 192.168.3.15. So this is your source and destination. So when the request goes to the IP table, when it goes to IP table of node 1, so sorry, so this goes to IP table. So here you know that there is a IP table on your node 1. So when it goes to IP table, it will see the destination, and because you have a cluster IP defined, so you define a cluster IP. That means there is a predefined route. So it is acting as a kind of a router. So it will go toward this 192 towards 192.168 3.18, and then from there it will go to this particular one. So here you see this acting as a service router. So that's why it is called as virtual service. It is going to, but this thing you can access only from within the cluster. Means you cannot go outside. If you want to talk to outside world, this particular cluster IP concept will not work. If you want to talk to outside, then in that case, so let's say your destination, for example, you have 192.168 3.7, and destination is, let's say, google.com. So your destination is internet. That means this packet first it will go to IP table. IP table. There you will define some service. So you define some service. Okay. That service can be of any type. Depends like what you are defining. See, in this case it is not cluster IP because it is outside communication. So here it could be like a node port, or it could be like load balancer, and then it could be your uh, fix name. So all of them are like, you can say, kind of router. You need to define either one of them. So if suppose you define something called node port. So node port is something that when the packet will come to this IP table, it will route to the service. So service suppose is node port. So it will tell to your, so here see what is happening. IP table is sending to your NIC port. You know the flow. IP table sends to NIC port, but this internally it refers to the service, which service you are using. So if it is node port, on this NIC port, you are going to get some dedicated port number. Dedicated port number. You're going to get some dedicated port number because every node, if you use this service called node port, every worker node by default will create some node port number. What you define, you need to define what kind of a port you want to have. So you suppose, let's say you define something called 3002. So every NIC port, there is a NIC port, there is a port created every interface. All the node will have this virtual port for your traffic. So when the traffic comes to this, from there it will go outside. So from there it will go to the external gateway. So from here it will go to the external gateway, and then from there it will decide what is the route for google.com, because you cannot have a direct route for google.com from your worker node itself. So you are going to have some external gateway. From there your packet will go to the external internet. So this is how this networking happens. See, it is not simple, but we need to spend some extra time on understanding each services, then only we can understand. It will take time. I mean, for in the first attempt, you will not be able to understand it. But this is a high level picture. I have one very good website. I will share you after this today's session. You can refer that website. It's very good site. It is explaining you how the packets are going outside your Kubernetes in case of external communication. So it is almost similar what I am telling you, but it's just in graphical way. I mean, I didn't prepare. Tomorrow I will because I will keep it handy and I will show you on the screen.
Okay.
Because today if I try to show it will take time. So this was on the networking part. Then we have something called storage. That is also very critical. Storage. So networking we try to understand what how the networking is working in the Kubernetes. Similarly, storage is also critical thing because if you see your pod, this pod, this pod has this pod. Whatever transaction this pod is doing, the disk of this pod is ephemeral. It has an ephemeral disk, which means the moment this pod is deleted, the moment this pod is deleted, this ephemeral disk will also be deleted. So, with respect to the pod life cycle, so pod life cycle, this ephemeral disk is also proportional. So, when this pod deleted, so let's say when this pod is launched, this storage is also attached. It is virtual disk of your pod. And when this pod is terminated, your storage is deleted. And this is I'm talking about only one pod. I'm not talking about the replica or I'm not talking about the restart. So suppose when you relaunch, or let's say restart, you get a new storage, which means whatever transaction your old pod has done, everything is lost. And this happens every time. Whenever Kubernetes takes an action on the pod, your disk is deleted. And this is one of the serious problem of container world. So it's not only for pod level. See, it is not pod level issue. It is your container level issue. If you see the design of architecture of containers are designed in such a way that they are ephemeral. Containers are ephemeral in nature. Means your CPU, RAM, NIC, and storage.
What is
The moment, yes,
what is
ephemeral
ephemeral?
means ephemeral is short life. So it
Okay.
is not a permanent in nature. It is binded with the container life cycle. So what happens when you start a container? So let's say when you run a container, you get resources. So you get CPU, RAM, then you get a NIC. Means when I say NIC means you get some IP, right? And then you get some storage. So storage is something you can say your container disk. So all these things you can see when you run a container, you get CPU, RAM, IP, storage. When you stop, so when you stop your container, you lose all four. When you restart, means you again start, then you get new container, new CPU, new RAM, new IP, and new disk. So here you get new storage, which means This disk is not same which was there previously. This IP is not same which was previously. So these two critical things. See, CPU RAM is fine. That is okay. If you lose it, not a issue. But if you lose IP and if you lose storage, then it is a big problem. This is a problem. See, whatever you have initially, it is not same now. So in the next cycle, if you restart your container, you get different IP and different storage. Means you lose everything in between. So in between, you lose data and you lose IP. So I told you about networking that Kubernetes has done this, solve this problem by allocating an internal IP to each pod, and then there is some internal communication. So every time if a pod is losing or restarted, a new IP is there, but there is a no impact to the outside world because you have something. So see, you have pod, you have pod, you have pod, you have pod, and then you have something called as service. In Kubernetes, you have service. So basically, you don't do it. Kubernetes take care. And then this is something called external, or you can say front end, and this is your backend. So on backend, if your pod is restarted, you get a new IP, but you are not concerned because this service is unique for you. This service keep a single IP, or you can say single gateway, single interface. So this is your single interface for your pods or your service. So here we don't say for pod, we call it a single interface for service. So whatever service you define or type of service you define, you get a single front end IP, single gateway, and then on backend there are so many IPs, and they keep on changing on day-to-day basis. These are pods. See, these are all are pods. This is pod. This is also pod. This all belonging to same service. So suppose you define a service called GUI IP, right? You define something called GUI pod. So for GUI pod, you have suppose four pods running. Tomorrow, if you add one more pod, so you have a replica. You increase your number of pod. Your outside is not concerned because outside it is single interface. So if you see the gateway or the root, there is a single gateway to outside world, but internally it has so many pods, but outside there is single IP. So this is how you resolve the problem of IPs. If your IP change, not an issue because you have someone who is doing this mapping continuously for you on real time. So if any pod dies on the real time, that IP is released and a new pod come in picture. So suppose here if we have 192.168.3.10, and suppose due to any reason this pod is restarted. So the next IP will be 192.168.3.15. It could be any IP. See, this is DHCP allocation. There is nothing called static or persistent IP. It is dynamically allocated. So a new IP will come. This IP, because previously this IP was communicating to the service. Now this IP will communicate with the service. So I hope you are understanding this thing. Let me try to understand, show some graphical way. One second. This is
So
called service. Yeah, please go ahead.
so the DHCP, where's that internal?
DHCP, yeah, DHCP, DHCP. It is called as dynamically. One second. I enable this thing. One second. Yeah. Dynamic host. So this is dynamic host allocation. See, full form I don't remember at the moment, but this is dynamically host allocation, host IP allocation. So what happened? There is some DHCP server, DHCP server. So you have a subnet, something like 192.168.3.0/24. So for this subnet, you have so many hosts. So you, suppose there are so many hosts. This is host 1,
So who
host 2, host 3, host 4. Yes.
who sets that up? You set it up manually, or it's
No, this is
it's on.
automatic. This is automatic. This is part of your Kubernetes. This DSCP is part of your Kubernetes. So this DSCP will check. So whenever a pod is launched, so if you see the call flow of pod deployment, so when a pod is deployed, so it will take IP. It will ask, it will talk to the DSCP server and say that give me an IP. So this DSCP server has a pool. Based on the pool, it will give some IP. So this allocation is dynamic. So it will say that okay, I am giving you this IP dot 3.5. This pod comes in picture, it will say, okay, I'm giving you IP 192.168.3.6. This pod is coming in picture 192.168.3.7. And it's not only your application pod, it is for the whole Kubernetes cluster. So this DSCP is not differentiating on the applications. It is like a common DSCP server for all the pods in the Kubernetes cluster. So in the Kubernetes cluster, there is a DSCP server. Whenever a pod is launched for the first time, it will talk to the DHCP server and ask for an IP. And this will give any dynamic IP available from the pool. So this pool, based on the IP which is available, it will provide an IP. So you don't need to be bothered about these IPs changing on the runtime because you know that you have something called service, right? You have something called service. So here you have a fixed route depending on what type of service you have created. So whatever service you create, like node port or load balancer or fixed name, see, depending on what type of service you are creating, it will on the back end it has something called as mapping. So let's say this pod is 192 because it got an IP from DHCP server. So this DHCP server gave an IP called 3.5, 3.5. And similarly to all the other pods. In runtime, if something goes wrong and this pod is, let's say, deleted. So once this pod is deleted, then a new pod is launched. Then you have a new pod. So here we have a new pod. So what will happen when this new pod will be launched? It will be talking to the DHCP server to get some IP. So it will get an IP. So let's say it get an IP called 192.168.3.59 depending on the allocation by the DHCP server. So there is no fixed IP. It is dynamically allocated IP. So this will join the service. So it will join the service. So this will become part of this particular service. So here this is removed and you have a new pod. On the front end, there is no change because your client is connecting on this particular service. So for you or you, when you go outside, you go from this service. So if there is an connection from outside, so from inside to outside, so from pod to another host or an outside world, internet, you will come to your service and then your service will take you to the outside. If from outside somebody is coming, it will come to your service and then service will internally take to the respective pod. You are getting? So in this way, you don't need to bother about the IPs which are changing on the runtime. I hope you got this point.
No, I got it. So if
Yes.
you need to change the IP address to a different network
Mm-hmm.
for your cluster,
Okay.
how's that done?
Need to change IP address for the different network. You mean that?
Yeah, for DHC. Say for example, you don't like 192.168. You want to change it to 10.1.
Okay.
That
Okay. Okay. I got it. See, from internal pod network, so there is something called as pod network. Pod network. This is your private network. And this network is never accessible from outside. So what I'm telling you, this 192.168.3 is a private network, and a pod is always allocated internal IP. Pod is never allocated any external IP. Means by default, Kubernetes will give a private IP to your pod, which cannot be accessed from outside. Now your question is that suppose I have a pod and this pod has multiple interfaces. So because if you see the default Kubernetes provides only one interface. So if I take only default case of a Kubernetes, my pod will get only one interface, only one NIC that I can say ETH0. And this ETH0 will have only IP from the subnet 192.168.0.5, let's say. This IP is coming from your pod network. So what is pod network? So when you deploy your Kubernetes, cluster for the first time, Kubernetes cluster for the first time, you need to specify pod network. So pod network is basically an internal IP range. So you can select 192.168, okay, 168.3.0/24, or you can select 10.10.10.0/24. It's your choice, and also Kubernetes supports dual stack. Dual stack means that it supports both IPv4 and IPv6. So if you enable both stack, then your pod will be allocated two IPs, one from IPv4 and one from IPv6. So your pod will get two IPs. Two IP will be allocated. This IPv4 or v6, this network you are specifying internally for the pods when you are deploying your Kubernetes. So this is not your application network. It is not your application VLAN ID. It is your Kubernetes internal private network. Now, if somebody want to go outside or somebody need to have a external connectivity, then comes your service. So there is something called as, so see what is happening. This is something called as service. Then you have external VLAN. Here you have external VLAN. External VLAN. Here internal you have something called pod private VLAN. This is pod private VLAN. This is always fixed. This is always fixed. So when you define during your deployment, so let's say you define 192.168.0.0/24. So always all the pods in that Kubernetes cluster will be getting IPs from this one. There is no, you cannot change it. You cannot say 172.168 or give some different IP. No, this is totally strict Kubernetes internal. This is Kubernetes internal. From application point of view, you can have a different VLAN for your different application. So suppose like you have team A pods, team A, team B, then you can say you have team C. So team A can have, suppose VLAN something called 10.10.5.7/26, and this can have 10.6.51.4/28, and this can have, let's say, uh, you say 172 168, then 5.5/30. So these applications have their different VLANs, right? They have different VLANs. But when you see this private pod VLAN, private uh, pod VLAN is always single for your Kubernetes cluster. So when the pods are deployed, so let's say this is your Kubernetes cluster. So this is your K8s cluster. You have so many pods running. You have so many pods running. I don't know which pod belong to which team. So let's say this is your green one. This is your green one. So the green one belongs to team A, and let's say this belong to team B, and then let's say this belongs to team B, and then we have something called team C. So team C pod. So here team C pod. But when you see this cluster network, this Kubernetes pod cluster network, it will be having a same subnet which you have used at time of your deployment. So suppose you used, for example, 0.0/24 for your pods. So internally, all the pods will be getting IP from this private subnet. But when you see these applications, so they may have their own service. So suppose this is service, this is service, this is service, this is service. So you have a service called So let's say this is in purple color for this team A. Then you have another service for this team B. Then you have another service called is the third one. Okay, slightly. So this is your team C. And in case team C has two VLANs, one is external, one is internal. So let's say this is not, let's say they have one is traffic and then one is, so I will say this is team A. Okay, this is team B. Then this is team C. Team C has two VLANs. One you can say ONM VLAN and one you can say you have traffic VLAN. Traffic VLAN. Now these services, and let's say team A, team B1 is your ONM. So this is ONM and this is also ONM. And now you know that these services, so there they will be mapped internally. So based on the service, so let's say for example this one, okay. So this will be internally mapped, this service. This will be mapped to here. Okay. Then you can see this will be mapped here and then this will be mapped here. Similarly for the orange one, not exactly orange, but yeah, for I can say saffron color. So this one. And then this green one. So you can see this green one. So this is your ONM. So this is your ONM. This is your ONM. This is your ONM. And then this is your ONM. Similarly, you have this traffic. So traffic will be talking to this one. Traffic will be talking to this one. Traffic will be talking to this one, and then traffic will be talking to this one. So this is how your communication happens. But internally, if you see the IP of pod, IP of pod is always 192.168.0.s. So this mapping which you are expecting for different VLANs is happening on the service level. So when you define your services, that is taking care of your translation. You got this, right? I hope you understood. This is how this conversion happens. But for pod network, IP is always unique and it is always from the pod network. It's not from outside.
Question.
Yes.
ONM. What's ONM?
Okay. This is operation and maintenance. Operation and maintenance. Just for using the normal day-to-day system administration activity. See, like if you see a server, so this is not Kubernetes, but it's a server, right? A normal server. Server has multiple IPs. One you can say is used for your task, admin task. Then you can say for your traffic processing, traffic task. Then you can say for your DB task, that if you have two databases you can use. Then you can say private VLAN maybe for clustering communication between different servers. Then you can say you have a backup VLAN, a dedicated VLAN for your taking backup, so that because of one task another is not impacted. Or if suppose your traffic is interface is down, you can at least log into your system. Database is not impacted by your traffic. Private communication happening between two clusters is not impacted. So you can segregate. But when you see Kubernetes, Kubernetes by default provides only one interface. Kubernetes will provide only one interface, and that interface is your private VLAN, and that private VLAN is your actually pod network. So a pod is always given an IP. That IP is from the internal network. So pod, you can never say that this pod is getting an external IP. This pod will never get external IP. It is something happening. The netting is happening, which you asked me last time. The proxy is there, which is preventing your internal IP. So basically, there are two things. Pod internal. So if you see this arrow, this is your outside world and this is your inside. So inside Kubernetes, you see so many pods running. These pods belongs to different applications. You don't know this pod is belonging to which application. But for Kubernetes, it is a pod. All these pods are from the same subnet. So same subnet. They are from the same subnet. But when you see from outside communication, because every application has its own VLAN and they have their own ONM VLAN, it can have own traffic, everything is separate. That is handled by the services. Services. They take care of this part. But this is strictly internal. Nobody can interfere here. Then what happens, as I mentioned you that Kubernetes provides you only one interface by default. But if you have a requirement where you want to have more than one interface for your pod, so suppose if you have want to have, so suppose this is your pod, and this pod got an IP, something called 192.168.3.5. This is interface. This is called as NIC1, and this is called as something. Let's say inside you see ETH0. If you're not happy with this, you says that no, I need more interfaces because I want to segregate my traffic. If you want to segregate your traffic, then you need to use CNI, container network interface. This is called as container network interface. Container network interface. For this, you need to bring external plugins. External plugins. For example, Istio. Istio is a service networking service mesh which provides inter-pod communication. So let's say this is your pod. There are four pods. Okay, your pod has one interface called as ETH0. There also you have something called as ETH0. There also ETH0, and this is ETH0. And if this interface has some IP 192.168.0.5. This is 192.168.0.6. This is something called as 192.168.0.7, and this is 192.168.0.8. But all these IP and interface belong to a Kubernetes cluster VLAN. Now, if you are not happy and you want to bring your own interface, because suppose your pod A want to talk to this is A, this is B, this is C, this is D. I told you that if pod A want to talk to pod B, C, or D, if it is within host, outside host, it will go to this ETS0, and I showed you the call flow. In that call flow, it will go to virtual interface, and then it from there virtual interface, it will go to the virtual bridge. From virtual bridge, it will go to proxy, and proxy to IP services, IP table and IP services. From there, it will land on the external node interface. But there is something called as Istio service mesh. Istio service mesh is something that in this pod only it will launch one container. It will launch one container. So there will be one container, extra container, which we called as sidecar. You remember sidecar? Side container. And then your pod will get an additional interface. This is called as ETH1. This is called as ETH1. ETH1. You will get an interface called as ETH1. You get an interface called as ETH1. This ETH1 interface is coming because of your Istio service mesh. Istio service mesh is something which create a mesh network so that your pods can talk to each other without using Kubernetes networking. So here you are not using the Kubernetes standard or default networking, rather than you are using this particular. Okay, let me draw it like this, then it should be fine. Yeah, this is ETH1 here. So now you can see that this inter-pod communication is happening with this service networking. So now I am not going to use the Kubernetes default network interface. So I'm not using this path anymore. I can use this path for maybe for some other purpose, but for internal pod communication, I'm going to use a different route. And that internal networking is provided by your Istio service, and it is outside your Kubernetes. So basically, it is a software. It is an open source software you deploy, you integrate with your Kubernetes. So internally, you deploy this, and it will create its own network. It will create its own network mesh, and then it will be providing you the connectivity between the pods. So this is one more way. If you want to have some more CNI, then CNI example you can have Multus. This provides multiple. Okay,
You have
multi.
OVN as well.
Sorry,
OVN.
OVN, Open Virtual Network. Possibly, but I'm not fully aware about this, so I will not be able to tell you. I need to check and then I will come back on this. So these are see networking, because if you are not happy with the single network of Kubernetes, because I told you the pure Kubernetes. See, this is pure Kubernetes. This is pure. Here you get only one interface and one IP, and that IP belongs to the subnet. That subnet is your pod network, which you have defined at the time of your deploying your Kubernetes cluster. So when you say 0.0/24, all the IPs, all the pods will be getting from IP from this only, irrespective of what application belongs, so like team A, team B, team C. See, whatever the pod you deploy, they will get same IP. This is from Kubernetes, but if you are not happy, you can create your service mesh. That service mesh will avoid using the Kubernetes root. So you can keep this root. This one you can keep it. So see, it's not doesn't mean that you don't use it at all. You use it. You use it for your external communication. You can use this for your external communication. This for external communication. So if you want to go outside, then you take this route and you come to your service. You come to your service. So this is your service, right? So here you define. So this is your service. You define, and then you can go outside. So from here you can go outside because you still need it. See, I didn't mean to say that when you use Istio you don't use Kubernetes networking. You need to use it. This Istio is only for the internal communication between pods, and this has its own networking which is not exposed to anyone outside. So for database replication or other things you can use this networking. I hope you understood this point. Okay. Coming to the storage part, see, I mentioned you that one thing is that your IP is deleted. Another thing is that your storage is also deleted. Means that whatever data you have stored in your container or your pod is lost when the pod is restarted. And this is the biggest issue with the Kubernetes. Not with Kubernetes, with the containers. And how Kubernetes has fixed this problem. So if you remember, I told you container plus Kubernetes. So both are different technology. This is different technology and this is different technology. Even though this technology is dependent using this container, it's something like you have container technology and then you have Kubernetes. This is your Kubernetes, which means Kubernetes is controlling your containers. So whatever issues or challenges you have with container technology, it is resolved in the Kubernetes solution. So Kubernetes is a manager which manages your containers. On layman language, if I say that Kubernetes is a manager, is a manager of containers. So the main job of Kubernetes is to manage your containers. This is the main function of Kubernetes. Now, how this storage is handled? See, this pod has problem that this disk, virtual disk of this container will be lost. the moment this pod is restarted. Then how Kubernetes will help me? Kubernetes will first create, it will take service from outside. So you see, this is your storage provider. This is your storage provider, and it can be, it could be anyone. It could be Amazon, it could be your Azure, it could be your Ceph, it could be VMware, any provider. This provider, and then I have my Kubernetes platform, or you can say my Kubernetes cluster. This is my Kubernetes cluster. So this storage provider is integrated with your Kubernetes, and whatever pod you are running in this Kubernetes, the storage gets attached to this pod. Whatever data you write here, it gets transmitted to the storage. It gets stored in the provider's area. And then this pod is restarted, you have a reattachment. You attach with the different pod. So let's say how it works. So you have a storage. This is a storage outside. Then this is your pod. So you have a attachment. So this is called as storage service. Storage service over network. So you use networking to expose your storage service. This is your vendor. This pod is attached. So whatever, so let's say it is attached something called as you say mount. Okay. Then you put internal disks like home. So inside your container you have something called home. Then you mount it to this external file. So it gets mounted to the external storage. External storage. So whatever data you are writing in home, it is going here. So whatever data you are writing, it is going to the storage. So suppose your pod is deleted. Due to any reason this pod is deleted. Then you have a new pod. Because your previous data was stored in the external storage. So this external storage will be mounted to this one, and then you have a new path. So this one when you mount, so your slash home, you see the old data. You see here old data. Why? Because this data was stored outside. So this is how you solve your storage problem. So what are the services in Kubernetes which are coming in picture? So this is your vendor. This is your vendor which is giving you services. Then this is your Kubernetes cluster. This is your Kubernetes cluster. Here you have what you do, you create persistent volume. So you create persistent volume over here. So when you create persistent volume, now you need to attach this persistent volume to your pod. So this is your pod. So you need to attach this to your pod. So when you attach to your pod, what happens that this persistent volume, so you have like say 100 GB, you create a 100 GB volume, 100 GB volume. When you attach it to your pod, this pod is ephemeral and you know that it will be restarted at any time without any intimation. It can start restarted due to any reason. So this persistent volume may be impacted. So to preserve this persistent volume, we keep the life cycle as separate. So there is something called system admin, Kubernetes system admin. So if you are a system admin of Kubernetes, you create a persistent volume, and then you create something called as PVC, persistent volume claim. So instead of direct route, there is something called as PVC. This PVC will be shared across pod. So let's say your pod is deleted. So this attachment and reattachment will be handled by this PVC. Instead, this PV talk directly, this PVC will take care. So here, how the route is this, like this, and here you can see on the back end, and this is handled by this. Suppose if some problem is coming, so you don't have a direct route, so you don't get a direct route. You don't create a direct route. Understand? So here you don't create a direct route. So you avoid this PV to be exposed directly to your pod. You have an intermediate PV. This is called as persistent volume claim. And this one is defined in your pod definition. And whenever you have a pod launch, it will be mounted automatically. And in case this pod is deleted, it will be deattached and attached back to the new pod automatically. So in this way, whatever data, so suppose you put some data, this data will be stored here. So when you put new data, data 2, this will also come here, data 2. Means whatever you are writing on your pod is directly going to your external storage. And in this way, you are avoiding your storage, your data being lost. So this is how you solve your problem of storage. So do you understand, Chris, this point, this specific point? See, this is
Yes, I
overall
do.
theoretical. Yeah, this is overall theoretical, right? So this is just theoretically. I'm not giving any practical demo, so might you might not be able to get it fully because you need to see how this is happening. If you have a lab, you can do some hands-on, and then you can see what I'm telling you. You can see this thing directly. But yeah, on the theoretical part, fundamental concept, if I talk about, this is how things work in the Kubernetes architecture.
Okay.
Okay, so this was about the storage. So let me summarize the theoretical concept. So I told you about IP networking in pod, right? So there we discussed internal, external communication. We also discussed about service. Service is an intermediate. Service is an intermediate between pod and outside world. So let's say if I have a pod, this is my pod, there is another pod. Then you have something called as service. And then from this service you expose to outside world. So you expose to anyone. So all the communication happen via service. Storage, I told you, this is storage. So you have extra provider vendor giving you external storage. Then you mount this storage to your pod. So you bring your storage, attach your storage to the pod. So this is your vendor storage. This is your vendor storage. When I say vendor storage, see this is external to Kubernetes. So you can have Ceph, you can create your private storage. You can go with AWS, you can go with cluster file system, cluster file system. You can go with, see, this and this are two software. If you bring your own hardware for storage, you can install Ceph or you can install cluster file system. Then you have VMware storage. That is again a software which you can install. This AWS, or if I say Azure or Google Cloud GCP, they are all public storage. This storage is exposed to your pod, to your pod. And if this gets deleted, this is reattached to the next pod. Or if you expand, like if you replicate, then you can attach to multiple pods. This is handled by your PV and PVC. So this is I told you about the storage. Then the third thing is about your Harbor. I told you Harbor is a repo of container images, repo of your container images. So when you deploy a pod on different nodes, so this is your Kubernetes architecture. Okay, so in this Kubernetes architecture, let's say you have node 1, you have node 2, you have node 3. So if you are deploying a container or a pod in specific node, so let's say you are deploying in this node, then you need image. Tomorrow, if you deploy here, you need image. If you deploy here, you need image. Basically, all the nodes need to have your latest copy of your images. So it is very difficult for you to manage images if you like store images individually in all the nodes. So storing images in all the nodes is not a good way. Rather, we have something called as external storage. So we call it as external image store. This is called as harbor. And then you provide connectivity to all the nodes. So let's say here you have this connectivity, here you have this connectivity, here you have this connectivity, and this harbor has all the images. So let's say it has image. So this is suppose image 1, this is your image 2, and this is your image 3. I want to download, install a container. So I want to run a container from image 3 in this node. Then what I need to do? So what will be the call flow? So when this request comes, then this particular node will be talking to the external repo. It will be talking to this external image store harbor. This harbor has this image 2, and then it will be downloaded to this particular node, and then container will run. Tomorrow, if node 3 I want to launch same container, then it will download from this path. Here it is maintaining build version, build release, you can say. So suppose today you store an image, it will say that release 1. Then tomorrow you update image, it will be called as release 2. And then if you update some more time, it will be called as release 3. So same image, you can see you have different releases. So what is the advantage if you want to do a rollback? Suppose you are here and you want to roll back. It is very easy for you. You just point out the release name, build number, and then it will automatically deploy your old image. So this is very easy. So for you, roll out and roll back, both are very fast. You don't need to take a backup, right? You don't need to take a backup of your images. Everything is maintained. So suppose you update your image, your old image is also there. It's just your, you can say, a build number. So you can retrieve any of your copy. You just need to specify the build number. So this is the advantage of using harbor. So again, harbor is outside to Kubernetes. It is not part of Kubernetes, I told you. So Kubernetes is very basic, very basic architecture. So this is the third point I wanted to tell you. In this only we discuss on the Istio and other things, right? Istio and Denim. But that we didn't discuss more in detail because that's a big topic that takes a lot of time. So is it okay, Chris? I mean, these 3 points are okay?
Yeah. Harbor.
Yes. Do you have a question
Harbor.
on this?
That,
Yes.
yeah, Harbor. Is that storage or
It is an image storage. Image storage that stores all the container images, all container images.
is that a software you install and then you put image on it, or it's a hardware?
Yes. It is a software. So Harbor is a software you install on the storage, and then you can see it is combination. So it has an API server. So what is there in your Harbor? So Harbor has an API server for front-end communication. Front-end communication. Then it has a database to store images. It is going to store images. So it has multiple components. It's but not big like Kubernetes. See, it is very small project, but it's very important for Kubernetes. So it will store images. It will be having an API server for communication, and this is a light version of. I mean, this is very light software. You install it. You need to install. You can install Harbor within your cluster, within your Kubernetes node, or you can install Harbor outside your Kubernetes. That is your call. I mean, that's part of your design. You can install Harbor software within your controller node also, and you can install Harbor software outside your cluster. Okay. Uh, Then, other than that, see, cluster architecture of Kubernetes, I explained you multiple times. So I assume you already understand the architecture. You understand the architecture now of Kubernetes.
So one thing,
Yes.
what's the difference in installing it inside or outside of Kubernetes? What's the benefit, Barbara?
See, there's no benefit, or it's just like your design, part of your design. Because see, if you deploy inside, it's just like it is going to consume your storage. It's going to consume your Kubernetes resources. If you deploy is at a separate node, then it will be like beneficial for you because communication is not a problem. All your worker node need to have a connectivity. See, there is an SSL based connectivity between an harbor and your worker node. So suppose this is your harbor and these are your nodes, Kubernetes nodes, node 1, node 2, like this and so on. So all these nodes to in order to download the images, they will be talking to this harbor. Right? They will be talking to this harbor. So this is your SSL certificate based login. Authentication is your SSL certificate. So that's the only, I mean, connectivity part. You can host this outside also. You can host it internally. That's purely your call. It's not mandatory that you put it inside. The only thing you need to consider is the connectivity. How you are going to provide connectivity between harbor to your nodes. So that's the only thing. Yeah.
Okay, got you.
Then architecture of Kubernetes and services we discussed networking, we discussed storage, we
One thing we didn't.
discussed, yeah,
One thing we. One thing we didn't discuss
yes,
is namespace in Kubernetes.
pod call flow, yeah, namespace, yes. Then we discussed this container technology, yeah, namespace. See, talking about namespace. See, this namespace is coming from your kernel.
Security.
It is coming from kernel. So if you remember, I'm going back to the old topic, old concept of kernel. See, you have an operating system, you have an OS, right? This OS is your worker node. Then your second node, this is node 2, this has an OS. And then another worker node, it has an OS. This is node 3. Now what happens? I told you in starting also, what is this containerization or what is your hypervisor? See, everything is oriented toward your Linux. So let's say this is your Linux kernel. Everything goes to the kernel, Linux kernel. So this is and this is. Here you have hardware resources, right? You have CPU, RAM, NIC, and then you have storage connected. All of them are physically connected to your operating system, to your kernel, Linux kernel. Provided if you install this Linux kernel in a full OS mode, it is called as OS. If you install this kernel, so the story is of whole about kernel. This is kernel. So if you install this kernel in OS mode, it is called as OS. If you install this kernel in hypervisor mode, it is called as hypervisor. Hypervisor. So you can see this kernel is a key player between whether it is an OS or it is an hypervisor. Hypervisor technology is applicable for your infrastructure part that we might have discussed. I don't remember correctly, but hypervisor is, see, it is a, I'm not sure we discussed in the starting, but I hope we discussed. So hypervisor part for kernel. So this kernel, so what happens if you define what is hypervisor? What is hypervisor? It is kernel plus software required for hypervisor. See, in the core, you have this kernel. What is an operating system? This is your kernel plus software required for OS functionality. So in the core, you see this kernel is common to both, whether it is hypervisor or it is operating system. Correct? So when you are working in a hypervisor mode, so what happens that this is your hardware. This is your hardware. When I say hardware, means physical root, physical root to CPU, RAM, NIC, and storage. Means there is a physical path, right? In your hardware, you have a physical cable, physical board, which is providing you the physical connectivity, physical path to your resources, CPU, RAM, NIC, and storage. Correct? Then you install some software. At core is kernel. Okay, the core it is kernel. On the core it is kernel. Depending on the mode which you have installed. So suppose you installed it in hypervisor mode. In hypervisor mode, then this will be called as hypervisor. If same thing, same hardware, you install this inside, you have this kernel, and you install. So this is your kernel, right? And you install in OS mode. Then this becomes your operating system, right? When it is an operating system and when it is an hypervisor, what is the difference? When it is an hypervisor, you can launch VMs, VM1, you can launch VM2, and then you can launch VM3 and so on, right? When it is in OS mode, you cannot do anything. You can simply run applications. You can say app1, app2, app3, correct? When the same thing, when you do this hardware, then you have this kernel inside, kernel on the core, and then you have this OS, but this is called as light OS. This is light OS mode. Light OS mode means very minimum software. Then you call it as OS, and you keep container runtime software plus container runtime software. Then what is the output you get? You get this is container 1, this is container 2, and this is container 3, right? So you can see three different scenarios and three different output. First one you see when you install in hypervisor mode, the same kernel is allowing you to run VMs. When you install in OS mode, same kernel is allowing you to run application or software. Same kernel when you install is in container mode, means you put some container runtime software, you run containers. Now, what is the difference in all three technologies? See, these are three different technologies. So, what is the core difference between all three of them? So, the core difference is that here, if VM1 want to talk to, if see, in all three cases, they need resources. Everybody need resources. They need resources. And you know what are the resources I'm talking about. This also need resources. So when I say resources, I'm talking about CPU, RAM, NIC, storage, four resources. Here also I'm talking about CPU, RAM, NIC, storage. Here also I'm talking about CPU, RAM, NIC, and storage. So you can see all three model. So we have three model. One is your VM mode where you have hypervisor. One is your second is your normal OS mode where you have application, and the third one is your container mode where you have a containers. All three of them, everybody need resources. See, that's the bitter truth. You run application, you run anything on top of your software, any kind of software. The software need resources, and these resources are lying here on the bottom. So these are the resources. So here you see this is your resource. Here is your physical resource: CPU, RAM, storage, networking, everything. Here is your resource. This is your resource. This is your resource. So you can see all three model, the way of getting resources different. Here if you see, so what happens if you want to get a resource? For example, VM1 want resources. So VM1 will come to the kernel and tell me that boss, I need resource access. Because it is an hypervisor, so kernel will say, I am going to give you a channel. Go and take resources. Suppose VM2 want access. So it will say, okay, it will come to your kernel and it will say, I need resource. It will say, okay, because you are a VM, I'm going to give you a channel to the resource. If VM3 want to access resources, it will come, then it will come to the kernel. It will come to the kernel. Kernel will say, because you are a VM, I'm going to give you a new path. So you can see that resource access is dedicated. VM1 has dedicated path for accessing resources. VM2 has dedicated part and VM3 has a dedicated part, right? Let's talk about this second mode where you have an application. So this application need to get resources. So what it will do, it will go to OS. It will say that I need resource. Now what OS will say, because you are an application, I'm not going to give you a direct route. I'm going to have my own route. So this has own route. So in this mode, it will be a dedicated route from between kernel and hardware. When this second application comes, it will say, okay, I'm not going to give you a dedicated route. You need to come to me. And then if you see the third application, you see this is coming. There is no dedicated route. So in the second mode, you see between your kernel and hardware, there is a single channel. Means these resources are controlled by your operating system. Your resources are controlled directly. When you come to container mode, when you come to container mode, here it will say, okay, come here, and then it will provide a channel. When you say, okay, I'm container 2, I also need access, it will say, okay, fine, I will give you a channel. If you say that so this is one, so this is container 1, so it will say, okay, fine, come here, and then it will give a channel. So you can see what is the biggest difference between first, second, and third. See, the biggest difference between first, second, and third is that the second method, which is your normal OS, is not a good approach because in second method you don't get a dedicated channel between your application to hardware. Here OS is your controlling factor. So if you go with the second mode, which is our normal operation, where we have a normal OS installed and then we install application, you land nowhere. But if you go in kernel mode, you are going to get a VM. My actual target is not a virtual machine. My actual target is the container. Because what is the difference between VM and container? VM you can say is bulky. So when I say between VM and container, what is the difference between VM and container? VM and container. This is bulky, this is lightweight. Here you need to follow L2, L3, L4 and L5 if you want to run an application. Here you need to only bring L4 and L5. Means this is light, this is bulky. Here deployment is faster in compare to bare metal. But here deployment is fastest. It is fastest because here you only run, no install. So if you see from Linux point of view, kernel point of view, 1 and 3 are similar. This second and third. So 1 and 3 are similar. The only thing is that in 1 you are getting VM and in 3 you are getting container. 2 is not useful because 2 is a normal OS mode that we don't follow. So here you see how do you get access to the resources. So here when you see this kernel is giving you access to your hardware, that means it is going to create. And how does kernel work? See kernel, how do kernel get a resource? So let's say this is a kernel. This is a kernel and whatever mode you have, irrespective it is like OS or hypervisor or you say container. You have three mode, right? This is going to get an channel to the hardware. So it is going to create a channel to CPU, RAM, network, and storage. See, if you have this two mode, so if you have hypervisor mode, if you have container mode, then you get separate. So let's say this is a box. So let me note. Okay, I'm saying fine. So let's say this is your hardware. This is your hardware. So it is going to call the resources. So how kernel will call resources? Kernel uses namespace. Namespace technology to call hardware resources. So kernel always uses a namespace for calling the hardware resources. So this is how where your kernel this namespace concept is coming. So namespace is a concept which is valid in your hypervisor. Namespace is a concept which is valid in your container. And namespace is a concept which is valid in your normal OS also. So whenever a kernel is calling resources, it uses something called as namespace. So this red color you see is called as a namespace. So here you see there are three namespace. This red one, yellow one, and blue one. So this is NS1, this is NS2, this is NS3. If you see this second one, there is application mode. Sorry, my mistake. I have drawn in the reverse direction. Okay, here between kernel and hardware. So this is called as NS1, this is called as NS2, and this is called as NS3. If you see normal OS mode, it is called as NS1 only. There is no separate namespace, only one namespace between your kernel and hardware. If you go with the normal OS, if you go with the container, then again you have called as NS1, NS2, NS3. You see, this is called as namespace technology. So suppose I have CPU. So let's say I create a table. So let's say I create a table. So I will say physical physical. Then I have something called CPU, RAM, NIC, and storage. Now namespace says NS. So let me erase this. We call it as namespace. Namespace. So I will say ns dot one. So it will be something like ns dot cpu dot one, or I can say, see, this is just a format I am telling you. It's not mandatory that it's the same. So I'm just giving you an example. See, it will be like ns one dot cpu, ns one dot ram, ns one dot nic, ns ns one dot storage. Okay. Similarly, if you create another namespace called ns2, so this becomes ns2.cpu, ns2.ram, this is ns2.nic, ns2.stg. Means if you have a same physical storage, you create a logical boundary. So for a same physical CPU, so you see here CPU is same. Here the CPU is same, but you have created two different namespaces. Similarly, you see this RAM is same, physically same RAM you are using, but you have created two different namespaces called as .ram. Similarly for NIC, so for NIC you see they have a same NIC but getting divided in two different NIC from kernel level. Similarly for storage, you get this one storage. So here you have storage. So same physical storage is being used with a different namespace. So this is called as namespace technology. If I talk about Kubernetes, so what is a namespace? So namespace, you can say on high level, the namespace of Kubernetes is for your resources. So whatever pods or your deployments or services, anything, any object belonging to your Kubernetes specific section will be defined, distinguished on the basis of namespace. So on the high level, the big namespace. So when we say ns, so when we say ns is equal to Krishna, so what will happen that Kubernetes will create a namespace Krishna. So suppose I have a pod in this namespace and this pod need to access resources. It will be saying that Krishna dot CPU dot, so it will say, so Krishna dot ram dot nic, means whenever this particular namespace, see, when I say namespace, everybody in that namespace will need to access CPU will be using the same channel which is specified. So whenever I create a namespace, there is a channel created on the background with the between kernel and the actual hardware. So your kernel will create a root and that will be called as a namespace. So you can give a name. So you can have multiple namespaces. So I hope you understood this point. It is
Yes,
a
I
way
do.
to call resources. Yeah.
Is there a way to see, like, the command line to see the namespace assigned
Yeah, there is a way.
to
Yes. You need to run this command called kubectl get ns. It will print all the namespaces. So Kubernetes has by default called as namespace. Default namespace. Then it has kube ADM. Then it has kube public. There are some namespaces which when you install your Kubernetes, you get. And if you don't specify any namespace, everything goes to default. So in Kubernetes, it is very important whenever you call Kubernetes, always give namespace. If you don't give namespace, your pod or your object will go to the default one. So you create your specific namespace. So let's say Krishna. So whatever pod I deploy here will be going to in this namespace, and it will be using that same channel, that channel which is meant for this specific tenant. So it is a tenant. Similarly, you can say it is a project. If you want to correlate, it is a project. So suppose your project has a namespace, then it will always use the specific route for talking to the hardware resources. So suppose you say namespace Krishna, then it will use this channel for accessing resources. If you say namespace is kubeadm, then it will use, so let's say the namespace name is kubeadm, and this namespace, let's say, is your Krishna. So whenever my pod is getting resources, whether it is CPU, RAM, storage, it is following this channel. If Kubernetes is accessing CPU, RAM, network storage for its own operation, it is using this channel. So this is basically a channel. How do you access your resources? Okay, Chris.
Yes. Thanks.
Okay, I think so. Concept-wise, we covered most of all the topics. So now we need to discuss on the practical part. So theoretically, I covered everything. Talking about the practical, so see, we need to see how to create a lab. So for creating a lab, so if you want to practice lab, okay, maybe I need to discuss about the theoretically lab deployment. How do you deploy a Kubernetes? Okay, no worries. So tomorrow I will tell you about the deployment. So what we will do tomorrow? So tomorrow we will talk about Kubernetes deployment.
Envy.
So
Okay.
it will be manual.
Mm-hmm.
Theoretically, I will cover automatic, and then third one is your company Kubernetes. So the company Kubernetes KTest deployment, which is, you can say, an automation of these two. See, this is very granular level on the services level. This is from Kubernetes, and this is on automatic. So this is like LCM, life cycle manager based. So you have life cycle manager based deployment, which is followed by the companies to avoid manual or deployment, to reduce the deployment time. So company follow their LCM based deployment. So we will discuss all three of them. Then we will see how to do the demo. See, to do the demo, so or to do practice, you need to either create your private lab, which you have your plan, right? You have hardware you want to deploy, and you can try some public platform, public lab.
Yeah. So the private
So yes.
so the private lab, I like to set up the Linux virtualization to
See,
deploy in that.
Linux, that Linux virtualization which you are talking is that you first, you have piece of hardware, right? You have hardware one, then you have hardware two, then you want to install hypervisor,
Yes.
then you want to install hypervisor, then on top of that you want to create VMs. So you create VM, so VM1, VM2, VM3, and then here you also create some more VMs. You create VM4, VM5, and VM6. And then you use this one to bring your cluster. So you say you create a cluster of Kubernetes, K8s cluster, K8s cluster. So this you want to achieve, right? This is your path.
Yes. Yes.
Yeah. So okay, that will take some time because let's first finish the standard Kubernetes, understand how this standard Kubernetes works or deployed. Then we will come to this your use case. Your use case is third one.
Yeah,
Okay.
because most companies go in three kind of thing.
See, this is again a topic of debate that in telecom we call it as CNA and CNB, means Kubernetes on VM, Kubernetes on VM, and Kubernetes on bare metal.
Okay, got you.
So if you follow this path where you have an hypervisor and then you install Kubernetes, means you are using two technologies. You are using hypervisor and then you are using Kubernetes cluster. There is one
Okay,
more way that in CNB you have a hardware HW1, then you have hardware HW2, then you install Kubernetes directly. This is called a CNB. Here you don't have hypervisor. So from performance point of view, administration point of view, complexity point of view, you don't have a hypervisor to be maintained, right? You have your own hardware and then you have Kubernetes running on top of that. Means you eliminate this extra layer of hypervisor. If you have a private cloud where you are building your own setup from hardware, then you have choice. Then always CNB is preferred because you don't need to maintain hypervisor. But if you have a public platform where you are getting VMs, then definitely you go with CNA because you don't have an option. Here you say CNA. This one is called as CNB.
okay,
So from management point of view or administration point of view, CNB is a better option because you don't need to pay for hypervisor. You don't need to have a system admin for hypervisor. Also, you don't need to have an extra layer of hypervisor. You directly utilize your hardware. So it's again your choice what you want to have. But yes, for your lab point of view, you can follow this one because you will get more virtual machines. So if even if you bring your cluster Kubernetes cluster, you still have some VMs which you can use for some other purpose. That's okay. See, for hypervisor, you can have OpenStack, you can have VMware ESXi, you can have VIO, again flavor of OpenStack, you can have Red Hat OpenStack, so many OpenStack. Or you can say hypervisor. Manual hypervisor means manual hypervisor means you have individual, this is isolated. So if whatever VMs running on this hypervisor 1 will be managed individually and whatever VMs running on hypervisor 2 will be managed individually. So here you can use KVM, that is a preferred one which is coming from the Red Hat, or you can say this is something like kernel based virtual machine. So it is by default present in your as a hypervisor in your normal operating system, right? So you can take this path. That's fine. So theoretically, we covered all the topics. We will now see how we can go with the practical one. Yeah, one theoretical topic left is your Kubernetes deployment that we will discuss tomorrow. So I will cover these two topics tomorrow, point one and point two. Point three, we will see how to handle it because we need to do the practical demonstration, right?